I got with me here some models, what we might call toy models, which consists of basically spherical metal balls to illustrate some of the concepts we are trying to understand here, which include defects in crystals. Specific defects we will focus on will be defects like grain boundaries, vacancies, etc. So you can see this model a little more, and I will show this from an alternate camera angle for you for better visibility. So what I can do to this model, which is nothing but two transparent sheets wherein I have filled some metal balls. I can shake this thing around, rotate it around, and of course try to simulate some of the conditions which would be found in a metal. For instance, suppose I am shaking this is something like thermal vibrations. So using this toy model, let us see how we can form some of the defects which we have been considering so far. So let me shake this a little bit, and then I have got now, for instance, a structure which I can show you in the other vision, which is the top camera view. So you can see here, these balls in this region are arranged in a perfect crystalline array, and this is my high pack density, which is the highest packing in 2 dimension, which is the hexagonal packing. Similarly, this region again is arranged in a perfect crystalline array, and this is a third region which is arranged in a perfect crystalline array. Between these 3 regions, for instance, of course you can consider some disordered region here. Within these 3 main crystalline regions, you can see there is a boundary. So this is what, like we will still define, can be called as a grain boundary. So you have a grain boundary which goes like this. This is one kind of a defect which we can nicely simulate using this toy model. So let me take this model and do a little more of shaking so that I can show you some more defects, and especially the formation of vacancies. So I have done some shaking here, and so try to create different kind of crystalline orders in these, and so let me get a perfect view for you wherein I can get a vacancy. Okay. So now, for instance, I have got a picture here now, and I will zoom in a little bit for you to show a better picture of this. So this is now my crystalline array of balls, and within this crystalline region, as you can see, this is my crystalline region, you can see 2 vacancies here. There are 2 vacancies here, and an important thing, of course, which an experiment we can do, keeping these vacancies in purview, that I take this model again and try to give some thermal vibrations to this. So, and then I put my model back, and you see, lo and behold, in spite of all the vibrations I gave, you see these 2 vacancies are still there. So this is something like we can visualize as equilibrium thermodynamic presence of vacancies. Of course, this is just a toy model, but still you can see that these vacancies are difficult to shake away and they persist, and this is taking analogy from our understanding of vacancies. These are like our equilibrium concentration of vacancies. So we can see that some small toy model like this, which just consists of some spherical metal balls between 2 perspex sheets, can actually give you a nice picture of what is a crystalline array and the concept of grain boundaries, etc. Apart from this model here, in which I showed you vacancies, I got a couple of other models. One is this model of a cube here, and this model of a cube shows, for instance, the presence of surfaces. So as I told you, any crystal, inevitably a real practical crystal, has to have surfaces. So for instance, this is my 100 surface of the simple cubic crystal. So this is a simple cubic arrangement, as you can see, and this is my 100 surface. Similarly, you could have other surfaces in the crystal, and later on we will make a relative calculation of the surface energies, for instance, in a copper crystal, which is not simple cubic, which is face-centered cubic. So for instance, this would be a 111 crystal. And if I look a little more carefully at this 111 surface and zoom in a little bit here, so you can see that this 111 surface actually has these atoms here. So these are my 111 surface atoms, and you can see that this 111 surface actually is more loosely packed in the simple cubic crystal as compared to the 100 surface. While in the case of later on, we have already made the calculation that in the case of face-centered cubic crystals, actually the 111 surface is the close packed surface and there is a higher density as compared to the 100 surface. Similarly, I can show you another surface of the crystal, which you can see in focus here, and this is now I cut my crystal like this vertical plane, and that means this is my 110 kind of a surface. Again, you can see this 110 kind of a surface has a lower density as compared to the 100 surface, which is not a close packed plane, but still it has a higher density than this 110 surface in a simple cubic crystal. So, we already made these calculations before to actually see some of these things, but this actually shows some sort of an what you might call a toy model of surfaces in a crystal. And now for instance, this 10111 surface has been disturbed. So, you can see that this atom has moved to a wrong place, and therefore, this can be thought of as a defect in a defect. That means, surface itself is a defect, and this surface has been defected by the wrong position of this atom, which of course, I can try to move back to its original place. So, these are nothing but magnetic metal balls from which I have made these models. So, let me show you one more defect, and this pertains to the question asked by Soumya in a previous lecture, in which here the defect I see in the center. For instance, let me move this model to the center. So, the defect I see in the center is actually associated with the rotational symmetry of this crystal and is actually what you might call a disclination. So, let me perhaps zoom out a little bit from this position, and you can see clearly that there is a pentagon in the center. So, the normal coordination, as you can see from this model on the left hand side, the normal coordination is actually in a preferred orientation, which I will bring the other model back to focus. So, the normal coordination is 6. That means, around any central sphere there are 6 spheres. This is what is preferred, and this I would call the normal crystalline array in 2 dimensions. But in this case, the normal coordination has been broken, and you can see there is a pentagon in the middle, and this is a defect associated with rotational symmetry of this crystal, and this I can call as a disclination. So, this is a nice model of a disclination, and as you can see, pentagons, when you talk about filling space with 2 dimensional figures, hexagons can fill flat space, that means Euclidean flat space, pentagons can fill spherical 2 dimensional space, and heptagons, that means 7-sided figures, can fill actually hyperbolic 2 dimensional surfaces. So, if I want to introduce curvature into a flat surface, then hexagons alone will not do. I need to introduce pentagons in the surface, and therefore, the introduction of this pentagon introduces curvature to the surface and makes it spherical. That means, I have got a curvature here. So, this is a nice model of a disclination in a crystal. The third model I am going to show you, perhaps is a little ahead, and we will come back to this later in the during the course of this lecture, is again a ball model in which I am showing a dislocation. This is of course a very crude model, it is not a realistic model of a dislocation, but nevertheless you can see that the crystal, if you look at this corner, looks perfect. The crystal here perhaps looks perfect downwards, but here there is an extra half plane of atoms, or you can otherwise think of it as a missing half plane of atoms at the bottom. So, somewhere here I can visualize this middle line where the pen is, I can visualize a dislocation line. So, this is my, of course, in 2 dimensions this is just a 2 dimensional crystal, therefore, this is a dislocation point, but in 3 dimensions suppose I had a crystal like this pervading many layers below, that would be a dislocation line. So, with these small toy models I can try to understand some of these simple crystals, and many of you can actually make these kind of toy models at home with these cycle ball bearing balls, and then actually try to understand some of these structures which form when you actually try to make a crystalline array. Before we take up defects in ionic crystals, let me revise some of the concepts we have been talking so far with regard to defects. We have been trying to classify defects based on dimensionality, their association with symmetry, based on their origin, based on their position, and the important question of course that how the crystal has been defined, and hence how the defect itself has been defined, has it been with respect to a geometrical entity or a physical property. The path to understanding defects, we said, was that we take up an isolated defect of course first, and then try to understand all aspects of this isolated defect. Then of course we try to ask that can this defect associate with other kind of defects of the same kind and different kind. We study their interactions, their binding energies, etc. Then of course we proceed to the more difficult challenging problem, which is not only a problem in terms of the difficulty in understanding, but also the difficulty in terms of the multiple length scales of the problem involved. That means that typically if I am talking about dislocations, I need to worry about isolated dislocations, I need to worry about dislocation cell walls, dislocation grain boundary interactions, etc., which would take us across various length scales starting from nanometers to almost microns. So, this is a kind of a multi-scale integration I would like to do, and in that case I am considering the behavior of defects under imposed constraints, which could be stresses or forces on the material, and also the collective behavior of many kind of defects interacting with each other. Okay. So, this is we said was the path to understanding defects, and we had especially in this context defined a term called the defect structure. So, now let us proceed to ionic crystals. Ionic crystals, as we know, have charged species, that means they have an anion and a cation, and therefore there are special requirements when we are considering defects in ionic materials, and we will note that suppose I leave some unbalanced charge in the material, then this is going to cost a lot of energy for me, and therefore in ionic materials charge neutrality becomes sort of a unwritten rule for maintaining low energy state. That means, and of course I do not mean the global energy minima, but what I mean here is sort of the preferred local energy minima. So in the context of ionic crystals, the overall charge electrical neutrality is an criteria which I would follow. The first defect I consider, which I think we did there was no analog of that, especially we did not consider that in the context of metals, is the Frenkel defect. In Frenkel defect, typically the cation gets displaced and gets into interstitial positions. Now what we might call this is, in terms of a normal terminology, is called a self interstitial, and the reason that self interstitials are not found in metallic materials, for instance, if I take silver or copper or one of these FCC materials, we had noticed that the enthalpy of formation of vacancy was the order of 1 electron volt. But suppose I am talking about a self interstitial, the energy is about 3 electron volts. So we see that it costs a lot of energy to put a self interstitial in a normal material like copper, and therefore self interstitials are not found in metallic materials under normal circumstances. Of course, you could always do an heavy ion bombardment or some kind of a non-equilibrium processing, which would take you to such a state wherein such kind of energies can be tolerated. So that will be a what you might call a high energy state as compared to the preferred state, which is of course the formation of vacancies. Now examples of Frenkel defect formation can be found in silver iodide and calcium fluoride, and if you notice the concentration, and later on we will make a calculation for instance the point defect concentration in a material like copper, even close to the melting point, and we would note that this concentration of Frenkel defects is much larger than that found in typical the vacancy concentration in metallic materials. So you can see in silver chloride is about 10 power minus 3 at melting point, and in AgBr is 10 power minus 2. That means this is a fraction of Frenkel defects as compared to the atomic sites or the number of cations in the material. So this is one kind of a defect wherein you can clearly see from the picture below that an cation which is supposed to sit in a sublattice of the cation has been displaced to an interstitial position. Of course, this is a schematic, and like many other pictures we will be presenting in this lecture, they will all be schematics. So we should not mistake them to be a true picture of the physical situation, wherein there will be other kind of displacements around the atom, and of course these are 2-dimensional versions. The real 3-dimensional structure could be slightly different. So using of course this schematic, we are understanding that how an interstitial, how an cation which is originally present in the its sublattice has been displaced and has moved to the interstitial position here. So this is from the original position. In this case, of course, I do not have to worry about charge neutrality because the species has not been removed from the system, and therefore in Frenkel defects the issue of charge neutrality does not arise because it is automatically charge neutral. The second kind of defect, which I think is a good example illustrating the basis of charge neutrality, is the pair of anion and cation vacancies. So if a single anion goes missing or a single cation goes missing, then you will have either a positive or a negative charge in the material. Okay. So cation will give you if a cation goes missing, then you will have a charge imbalance, and similarly if an anion goes missing. And these Schottky defects are typically found in alkaline halides. But suppose I have now a cation and an anion missing together, then the system charge is maintained neutral. So this is called a Schottky defect, and obviously there is no analog of this in the normal metallic materials which we have considered before. So the Frenkel and Schottky defects are two common defects which are discussed in the context of ionic crystals, but then we have many more possibilities. So let me just revise these two important defects. In the Frenkel defect, you have an interstitial typically of the smaller ion, which is the cation. Of course, in theory, of course, you could also consider an anion interstitial, but as you can see, the anion is much bigger in size, and hence it is usually the cation which gets displaced to the interstitial position. The second important one being the Schottky defect, where you have a pair of anion and cation vacancies typically associate with each other, because now if they are well separated, then they would tend to get associated because of the charge associated with these kind of defects. There are other possible defects in ionic materials. The list is actually very long, but we will take up a few illustrative examples to understand some other defects in charge materials and in ionic materials, and especially the concept of charge balance in these materials. Now for instance, suppose I have a sodium chloride crystal, and instead of a positive monovalent ion, in one of those sublattices I have a divalent ion. For instance, the example I could consider is if a sodium ion is replaced by a cadmium ion. So the cadmium is 2 plus, and suppose this is my site where the cadmium ion sits. So this is my site, Cd2 plus. So that means there is an extra positive charge which has been added to the system. To compensate the charge, typically a cation vacancy has been created, will be created. That means that now if there was 1 M plus, instead of that I put 2 M plus, the 2 M plus compensates for charge of 2 metal ions, so say sodium plus, and therefore one of these sites is left vacant, so that I can have a charge neutrality. So this is another possibility when it comes to ionic crystals. That means you have a ion of higher valency replacing an ion of lower valency, and correspondingly to maintain charge neutrality the number of ions of that type go missing. So this is another simple possible defect in ionic materials, and of course it depends on the particular system. Like for instance, I am talking about sodium chloride, or I am talking about potassium bromide, that which kind of a defect is lower in energy and under what circumstances those defects have been produced. So many of these could be non-equilibrium defects, and they could be annealed away when you wait for at a certain temperature for a long time. There could be defects which are arising out of off stoichiometry, and later on we will discuss this again once more in these kind of defects in the context of structural point defects. So that aspect we have already discussed, that how some of the defects could play a structural role, and we call them structural defects, and we will come back to this topic of stoichiometry in that context. But here we will consider the experiment wherein zinc oxide vapor has been heated in zinc vapor. That means the zinc now, which is now in the vapor form, can be incorporated into the zinc oxide crystal, and the stoichiometry is of the compound will be affected, in that more and more zinc is being incorporated into the material, where now this Y is greater than 1. That means there is a zinc excess in the crystal. This excess cations occupy interstitial void positions as shown in the figure below. For instance, now this zinc would go into interstitial positions. Now remember that this is a cation and smaller in size, and therefore based on the principle we saw before, that it is actually the cation which can sit in interstitial position. Similarly, the zinc can also sit in an interstitial position. And to maintain charge neutrality, the electrons associated with zinc, for instance now zinc can give 2 electrons, they stay close to the zinc. So it is not just a zinc 2 plus ion which is sitting there, it is a zinc 2 plus ion with electrons associated with that zinc 2 plus, which are created from the zinc 2 plus, which sit around this interstitial position. Therefore we maintain charge neutrality in this system. So as you can see, not only can there be self interstitials, but there can be interstitials of this type, which in some sense is a self interstitial, but which is coming from off stoichiometry. That means I have incorporated more zinc than the sublattice can allow, and therefore this extra zinc cannot sit in the sublattice position and has to go into interstitial positions. And to maintain charge neutrality, this interstitial defect is also associated with electrons. So this is a possibility in ionic materials. There are other defect considerations for configurations. For instance, there are 2 which are shown in this slide, and as again I point out that many of these are schematic diagrams and they should be interpreted appropriately. So for instance, here I have 2 configurations, one in which there is a cation and an electron, and other case there is an anion and a hole. So this cation, and when is this kind of a configuration possible, wherein instead of an M plus ion I have an M2 plus cation which is present in the sublattice. That means now this is a defect in the cation sublattice, and now because now it is a 2 plus, for maintaining charge neutrality there has to be an electron present, and this electron is typically localized around this M2 plus ion, giving me an overall charge neutrality. So this is a defect configuration in which there is an electron present near an cation defect. So this is an cation, for instance this could be divalent cation with an associated electron. The other possibility is, of course, I could have an instead of having a monovalent, for instance an example, a monovalent anion, I could have a divalent anion. In this case, to maintain charge neutrality I would need a hole. So this would be an anion and a hole combination which is giving me my charge neutrality in this system. So these are 2 nice examples. It is an cation sublattice defect with an electron, or an anion sublattice defect with a hole. So, these are two possibilities, and obviously this will show up, these electrons, additional electrons and holes will show up as additional states in the band diagram, which would correspond to additional resonances and absorption. So, this you can actually experimentally investigate these structures. There is an important kind of defect in the context of ionic materials, and this is important because often these defects impart color to the material, and therefore they are called color centers. So, and the typical name used for them, so for instance, they are often called the F centers. So, let me write that down. For instance, these color centers are also sometimes called the F centers. So, these color centers, and they would impart color to otherwise a normally a transparent kind of a material which does not absorb in the visible region. So, let me take an example here. For instance, now this is for instance an MX kind of an ionic crystal, and what happens is that you have an anion vacancy. Now, to maintain charge neutrality, the anion vacancy traps an electron. So, you have a trapped electron in the position of an anion vacancy here, and this trapped electron of course gives you a charge neutrality, but additionally what you might call gives a separate level in the absorption spectrum, which would correspond to a few electron volts. So, the typical absorption center for F centers is listed in this crystal. For instance, lithium sodium chloride would have a 2.7 electron volt absorption band or absorption level. Now, of course, I will make a calculation here to show that actually this kind of an few electron volt level actually corresponds to the visible spectrum, that we will do below. But an important point to be noted is that in this schematic diagram, in for instance this MX crystal, M plus X minus crystal, I have shown an anion vacancy, and the anion vacancy has been shown to have an electron present which has been trapped there. But typically the electron distribution is not like the way it has been shown here. The electron density is more around the, not exactly at the position of the vacancy, but around the atoms, the ions which are surrounding that. So, it is something like this. So, there is an sort of a charge distribution around this center level, and maybe I will use a board to actually maybe a slightly better picture than one I have drawn here. So, suppose now I consider my 4 cations here, and now I need to worry about the electron distribution, and suppose this is, I use a red color chalk for that. The electron density maximized does not lie in the center, it actually lies a little bit toward the sides. That means that more it is pervades more towards these kind of crystals here, these positions. I would have some sort of a distribution which is around the and localized more towards the cations. So, I would have a larger density distribution, and this is to be expected because now this electron is present actually to neutralize the charge present on the cations. So, this is why it is present, and therefore, you would expect the delocalization of this electron charge density distribution. So, and a good example of such an F center would be the F center in CaF2 crystal, wherein it imparts violet color to the material. So, in this case of course, you have a cation which is associated with the electron in the sublattice, and of course, as I pointed out, it is not localized to the sublattice, but it is a center of some sort of an center of gravity of the electron distribution, which is the position of the lattice point or the missing lattice point where there is no atom. So, I was telling you that these F centers are important because they impart color to the crystal, otherwise some of them are very transparent crystals, like sodium chloride is a transparent material. Now, let me make a calculation to find out for instance for the example of potassium bromide, which has a about absorption level of about 2 electron volt. So, I can see that E equal to h nu, that means E equal to h c by lambda. E the absorption is 2 electron volt, which I have to convert into joules by multiplication by the charge of an electron. The lambda of absorption of KBr I can write down from this equation above as this is h and c, and this is 2 into the conversion factor for electron volt to joules, which comes out to be about 6.2 to 10 power minus 7 meters, which is about 620 nanometers, which is in the red region of the visible spectrum. So, you can see that suppose I have F center in potassium bromide, then I would see that the color, sort of a reddish color has been imparted to the potassium bromide crystal, and this is because of the presence of this anion vacancy, which is now associated with an electron density around it. The visible spectrum, of course, as we know, is from about 390 nanometers to about 750 nanometers. This is close to, of course, the red region of the spectrum, which is at the larger wavelengths. So, F center is one possible defect which is could be present in ionic crystals. Then we have to note that there could be a series of these kind of defects wherein these F centers get associated with each other, and there could be complications where one kind of defects get associated with other kind of defect in an anionic crystal. One example we will consider later, which is an example of such an association, but an immediate example I can cite, which is called the M center, which is nothing but an association of two F centers. So, if you have two F centers, which is called an M center, you have an F center localized on this position of the center of mass, which lies in this position, and there is an F center again which is located in a neighboring position, and this kind of an association is called an M center. And as I pointed out, there could be association of 3 more and association of these F centers with other kind of defects in ionic crystals, which would actually could lead to more complicated situation as far as defects in ionic crystals go. So, before maybe we should take up the structural point defects, let me summarize some of the examples we have considered so far with regard to ionic crystals. We considered the Frenkel defect, which was not associated with any kind of issue with respect to charge neutrality, which was nothing but a cation interstitial. The Schottky defect again had an anion and a cation vacancy which are coupled together. We also talked about for instance a divalent cation replacing a monovalent cation, which is now associated correspondingly with a missing cation in a neighboring position. We also talked about off stoichiometry, which could again give rise to interstitials, now which are of course neutral interstitials, but they are again associated with charge around them, that for instance zinc 2+ associated with electrons around them. We also considered defect configurations where there are anions and holes present, or cations and electrons which are present, which have localized to lattice positions or sublattice positions. The more colorful of these was this F center, and we saw that how, for instance, in KBr the F center gave rise to an absorption in the red region of the visible spectrum. And we also saw that these kind of defects could actually get associated and give rise to more complex configurations of defects in ionic materials. So, let us take up this concept of structural point defects, and in principle, of course, any kind of defect could play a structural role, but in this specific case, for instance, we are considering structural point defects. We already cited this example of nickel aluminum NiAl, nickel aluminide, wherein which had an ordered B2 structure, wherein aluminum rich compositions result from vacancies in the nickel sublattice. So, this example we already seen, and this was an example of a structural point defect in an metallic kind of a material. In an ionic analog of this, for instance, let me take the example of ferrous oxide Fe2O, and this has got an NaCl kind of structure, which is, as we know, two interpenetrating FCC subcrystals or FCC sublattices decorated, one with sodium ions, one with chlorine ions, or in this case Fe ions and oxygen ions. Often it happens that some of the Fe is present as in the Fe3+ state. So, correspondingly some of the positions of the ion sublattice are vacant. So, if you have some of the ions which is now in the Fe3+ state, correspondingly some of the positions on ion sublattice are vacant, and this of course because of charge neutrality, and this leads to off stoichiometry. In other words, now you could not have an ideal composition of Fe2O, and you could actually have a or FeO if I think there may be a small mistake here, and this concentration X can be as low as 0.9, and this now the vacancies which are coming in this crystal, of course these vacancies would come in the ion sublattice, are not because of thermodynamic equilibrium criteria. This is coming because of off stoichiometry, and this would therefore constitute structural vacancies. Another example would be in a sodium chloride crystal. Suppose I replace the calcium 2+ impurity, there is a vacancy in the sodium plus sublattice, and this vacancy again is a structural vacancy, and therefore the more I add the calcium impurity, the more of the sodium would go missing, and this is not coming from thermodynamic considerations of equilibrium, but because of the off stoichiometry I am considering. and in this case of course the stoichiometry is going from a pure sodium chloride to sodium sort of a calcium chloride kind of a structure. Another example of void stoichiometry is perhaps the same, it's a different version of the example I considered above, which is the ferrous oxide, in which case what happens if FeO is heated in an oxygen atmosphere, then you find that the stoichiometry is disturbed from Fe1O1 and X in this formula of FeO can be less than 1. So, there are vacant cation sites which are present, which you can see in this illustrative example. For suppose I have an Fe3 plus ion sitting instead of an Fe2 plus ion, which is now shaded in green. Correspondingly, you have some of the, and this is the normal lattice position is occupied by an Fe2 plus ion, which has been shown in blue. So, you would find some of the cation sublattice positions are vacant, which is actually coming from the off stoichiometry. So, therefore, for every vacancy in the of ion cation, 2 ferrous ions are converted to ferric ions, provides 2 electrons required by the excess oxygen. So, this is again coming from charge neutrality, but the origin of all these defects happens to be structural, which is off stoichiometry. Now, the next topic we consider, and perhaps the best example of defect ordering is point defect ordering, wherein it is easy to visualize some of these concepts, and I will take up perhaps a schematic example to show you what I mean by this point defect ordering and how this can actually change the symmetry of the structure. And this perhaps for instance can serve as a template for understanding other kind of defect ordering, like for instance stacking fault ordering, and even in under circumstances dislocation ordering. And this is coming from the classification in which we talked about as a defect as a random or an ordered kind of a defect. And the important point to note why this ordering phenomena is very important is that ordered vacancies, like other ordered defects, play a very different role in behavior of material as compared to a randomly present defect. And this is something which we need to note, and this will become obvious when we talk about the ordered defect configuration. So, let me take up a perfect crystal which is there on the left hand side of this figure. So, this is again a schematic wherein you see 2 sublattices, one red sublattice and one grey shaded sublattice. There are 2 subcrystals which is they are interpenetrating. Origin of one is at 0 0 0, there is half or 0 0, and the other one is half 0 half half. And now I introduce some vacancies into this crystal, and as you know, these vacancies could be introduced purely because of thermodynamic reasons, and now you have these vacancies introduced in various positions in this crystal. So, let me mark these vacancies. For instance, there is a vacancy here, there is a vacancy here, and there is a vacancy here, and there is a vacancy here, and so forth. And these vacancies are obviously now structural vacancies, because once these vacancies are introduced into the sublattice, the crystal goes off stoichiometry, right. And this very reason these vacancies could be present in this material. For instance, suppose I am talking about a disordered crystal, then these vacancies could be thermal vacancies, but suppose I am talking about an ordered crystal, this could be coming from off stoichiometry. If they are thermal vacancies, then of course these vacancies could also be present in the other sublattice as well. Of course, the energy of these 2 sublattices may not be equivalent, but anyhow because of the thermodynamic vacancies could also be present in the other sublattice. But if they are coming from off stoichiometry, they are localized to the for instance, in this example shown, it is localized to the B sublattice. Now, if I want to describe this in my language of probabilistic ordering or a statistical ordering of this crystal, so one sublattice is purely occupied by completely, for instance, this is my A atoms or ions, and the other sublattice is not occupied by an atom or a pure atom and an ion, but actually, for instance, suppose I am talking about a concentration which is 1/6, then I can talk about, for instance, 5/6 is an atom and 1/6 is a vacancy. So, this is a statistical picture of the occupation of the B sublattice. Now, though this is now one, so this is an important consideration, and to be kept in mind is that one sublattice is purely occupied by A, the other sublattice is now disordered with respect to the vacancies. That means a vacancy could be present in any one of the position of the sublattice, and actually they could move from one position to the other as well. And this can be described by a statistical picture as shown here for the example of about a concentration of 1/6 of a sublattice position of vacancy concentration. Now, there is a possibility that these vacancies can get ordered. Now, obviously they would get ordered in the B sublattice. Now, when they get ordered in the B sublattice, for instance, and this is now my disordered, for instance, what would my disordered structures unit cell? The disordered structures average unit cell will be a structure which is shown here on the right hand side. This is my average unit cell, wherein I have A atom located at the corners, and I have what I may call a B and a vacancy combination, statistically 5 6 then 1 6, occupying the central position. Because this is just a specific example, this would depend on the concentration of vacancies. And of course the pure crystal would have a unit cell as we normally know. This is my pure crystal's unit cell, wherein A's are located in the corner and B's are located in the center of the unit cell. Now there is a possibility that these vacancies get ordered on this B sub lattice, and on the left hand side I see here, left hand below picture, the vacancy ordered phase. And in the vacancy ordered phase, you can see that I am just considering example, this is just a schematic example. For instance, now if vacancies get ordered in every 1, 2, 3, 4th position on this direction, and maybe just the 2nd position on this direction, typically of course they could all both be equal. I am just considering a example just to illustrate the symmetry lowering which is caused by this kind of a vacancy ordering, but typically the vacancy ordering would lead to in such a structure with a unit cell which is a square unit cell, but you can see I am just considering a rectangular unit cell. And now if I am talking about a fundamental lattice translation vector, then in the case of a disordered crystal, my lattice translation vector would have gone from the corner to the center. So let me draw this using a ball pen. So this would be my fundamental lattice translation vector, okay, or in this picture here, this would be my lattice translation vector. But in the case of this ordered phase, you can see my new unit cell would be the one which is now which I am shading here. So this is my shortest lattice translation vector, and you can see that the vacancies have got ordered into a sublattice of themselves, right. So I can now talk about this structure in terms of 3 sublattices, one with A atoms, one with B atoms, and one with vacancies. So this is now a vacancy ordered structure, and now if I had such a structure, then I would have, for instance, not a small unit cell but a larger unit cell which is shown in the blue outline. So this is my new unit cell, which is of course got a periodicity of 2A in the original in the y direction and 3A in the x direction. So this is perhaps an sort of a schematic example of an vacancy ordered phase, and this illustrates the important concept that when defects get ordered, they get incorporated into the crystal structure. In that case the symmetry of the structure changes, the properties obviously would change along with the structure itself. And in this case, like in case of normal ordering, suppose in the normal ordering we would consider instead of vacancies the atomic species. So because of this ordering now of vacancies, you can see that the symmetry has been lowered, and my unit cell to describe the structure also change along with this ordering process. Examples of vacancy ordered phases can be found, for instance, in vanadium carbide. There are 2 examples listed here, V6C5 and V8C7. They can also be found in aluminum, copper, nickel kind of systems, and in some of the examples, for instance, vacancy ordered phases, you can correlate the vacancy ordered phase as what one might call as quasi-periodic superlattice approximants to a something known as a one-dimensional quasi-crystal. So these structures are very interesting structures, wherein now not only vacancies play a role as if they were elements or they were species in themselves, they also have interesting connections with other structures like quasi-crystals. In this example we have considered, we should of course note that again to emphasize an important point, for instance the A sublattice could also have vacancies. Some of these vacancies could be thermal vacancies, and some of the others could be structural vacancies which are now localized on the B sublattice, and of course B sublattice also could have thermal vacancies which would remain, for instance suppose even if we are working on stoichiometric composition. Now the vacancy is in the B sublattice, and if it wants to jump to, for instance, a position in the A sublattice, which would mean that an anti-side defect would be created, the 2 positions for the vacancy are non-equivalent. So that is something which we have to note, and this would cost energy. And suppose I am talking about diffusion of a substitutional alloying element, then you would notice that this vacancy has a different role to play than a thermal vacancy, which could reside either in the A sublattice or in the B sublattice. Okay. Of course, in any case, if a vacancy jumps from the A sublattice to B sublattice, which would mean an exchange of an atom with that sublattice, an anti-side defect would be created, and that would be energetically unfavorable. But the important point to be noted here is the fact that this vacancy prefers to sit energetically on the one of the sublattices. So, that is an important point to be noted, which is different from a normal thermal vacancy which could sit perhaps on both sublattices. After having considered some of these isolated point defects and also of course talked a little bit about the possible associations some of these defects can have, let us take up some examples of association of point defects, and we have to note that point defects and again the behavior of isolated point defects could be very different from an associated point defect. So, that point has to be noted. For instance, suppose two vacancies get associated to form a divacancy, then and this would typically involve something known as a binding energy, and for instance this could be of the order of about 0.3 electron volt in gold. Now, if you want to dissociate this divacancy, that would cost me energy. So, this divacancy once formed could be stabilized because of this binding energy. Of course, the question I would have to ask myself is that at any given temperature, how many of these vacancies are present isolated vacancies and how many are divacancies, because once I have a divacancy, then it lowers my configurational entropy of the system. So, at higher temperature I would assume that, or it would be a reasonable assumption to make that there are more vacancies which are isolated, and at lower temperature there is a better possibility for association. Okay. So, when I am talking about understanding these kind of defect association, I have to worry about enthalpic and entropic effects when I need to worry about, when I need to consider association of vacancies. Then the reason of course vacancies get associated is that they give you a certain energetic benefit, and the way to nicely visualize that, for instance, suppose I am talking about an isolated vacancy, two isolated vacancies, there are a number of bonds which are broken, and if these two vacancies can get associated with each other, then the number of bonds broken would be reduced. So, this is an easy nice way of visualizing why divacancy should form, and this energy benefit, as I told you, is called the binding energy. And as I also pointed out, but once I have this divacancy formation, then it reduces the configurational entropy of the system. So, as a function of temperature, there would be a certain not only an equilibrium concentration of vacancies, but also an equilibrium concentration of divacancies, and I would expect that with increasing temperature the divacancy concentration would increase. As I talked about divacancy, you could have a formation of a trivacancy and higher order associations, and in the case of non-equilibrium systems, a very nice example would be the formation of an entire region in a, for instance, in a crystallographic plane, for instance in a copper, wherein we have a full what you might call a plate of vacancies or a disk of vacancies, which we of course will take up later when we talk about the concept of dislocations and the concept of frank partial dislocations. Similarly, an interstitial atom and a vacancy can come together to reduce the energy of a crystal, and this is again obvious. For instance, where a vacancy and interstitial atom, one associated with one kind of a strain, the other with the other opposite kind of strain, and their association would overall reduce my energy of the system, and they would like to come together. So, this is an obvious case of defects of opposite type wanting to come together to each other. And as I mentioned, if I have a non-equilibrium concentration of for instance interstitial vacancies, of course interstitial in one system, vacancy in another system, then they can also come together and form clusters. And for instance, and the important thing, as I pointed out, is that some of these associations can be spoken about in a totally different language, like a prismatic dislocation loop in the case of vacancies, which is nothing but a disk of condensed vacancies, which is now a non-equilibrium concentration of vacancies, or in some cases as a stacking fault tetrahedron. So, these are some case wherein there are association of vacancies. The important point to note is that not only point defects can get associated with themselves, but they can also get associated with other kind of defects like dislocations and grain boundaries, and this again would lead to the lowering of the energy of the system in many cases. So, we start with isolated point defects like vacancies or interstitials, then we worry about their associations, like how vacancies can get associated with other vacancies, or how vacancies can get associated with interstitials, and how this now affects my energy of the system, which is I talk in a language of binding energy of these two defects, and also worry about how this is going to affect my entropy. And when I am talking about a point defect association, obviously the effect on entropy is going to be profound. And later on we will see the importance of association of some of these defects, for instance how an interstitial atom like carbon can get associated with dislocation and how it affects my stress strain diagram, and or how their association with grain boundaries can be for instance in many cases very deleterious. We will take up one example of a complex point defect formation, and as I pointed out, there are very many such possibilities, and we just taking up one example to illustrate the what you might call the path ahead, in which you can go into more and more difficult and more complicated examples. Now, and this the example I am citing are the case of the structural vacancies, and so the defect structures in ionic solids can be much more complicated than the simple picture we have seen some of the examples before. And one example, of course, one possibility we consider here, which is the case of this transition metal oxide, wherein the composition is variable. For instance, in nickel oxide and cobalt oxide, the deviation from stoichiometry could be pretty large, which is about 1 in 100 or 1 in 1000, and this typically is accommodated by the introduction of cation vacancies. In iron oxide, for instance, again we have previously noted that there could be large deviations from stoichiometry. In iron oxide, at temperatures greater than about 570 degrees, the stable composition is about Fe1 minus XO, in which X could be 0.05 to about 0.16, which is a pretty large number for a number of cation vacancies we are talking about. So, such a deviation in principle, of course, could be accommodated by Fe2 plus vacancies or O2 minus interstitials. And we already noted that the cation anion is much larger and would not prefer to sit in the interstitial position. So, this part we have noted. The real picture, of course, is much more complicated than a simple picture of just a cation vacancy or an anion interstitial is, and the name given to it is typically it is called a 4-1 cluster. So, the real situation is more complicated, and the defect which actually forms is something which I will show in a picture in the next slide, is a 4-1 cluster, where 4 Fe2 plus vacancies as a tetrahedron and Fe3 plus interstitial at the center of this tetrahedron are accommodated, and there are additional Fe3 plus interstitials around this tetrahedral configuration. And the story does not end here. If you have an F4-1 cluster, actually they can form larger clusters or larger association of defects to form something known as a 6-2 or a 13-4 aggregates. So, you could have an isolated cation vacancy, you could have association of these kind of vacancies, you could have for instance, and one association in this example is the formation of this tetrahedron and associated Fe3 plus interstitials, and this whole complex itself can get associated and form larger clusters, which would then of course be even more difficult to understand. So, an ideal geometrical representation of the defect we are talking about, which is now the 4-1 cluster, I am talking about the 4-1 cluster, and this is an ideal geometrical representation. This consists of some Fe3 plus interstitial at the center of this tetrahedron, and the Fe2 plus vacancies are at the, so these are my Fe2 plus vacancies which are present at the vertices of this tetrahedron, and because these are missing sublattice positions, so these are Fe2 plus vacancies around this central Fe3 plus interstitial, and this Fe3 plus interstitial at the center of the tetrahedron. And to maintain charge neutrality, additional neighboring Fe3 plus interstitials are also created. So, this whole cluster would now constitute my 4-1 cluster, which includes this additional neighboring Fe3 plus interstitials, which have not been shown in the figure. So, as we can see that the defect picture in ionic crystals can get actually very complicated, but in reality we have to understand these defect picture if I have to now understand, for instance, the absorption spectrum from such a crystal or the color imparted to such a crystal, and many of the other properties which I would want to know about these crystals. Before we come to a close of consideration of these point defect chapter, one important question we can ask is that how can I produce these point defects? One example or one case we have already seen is the natural production of these point defects because of thermodynamic reasons, which is the entropically stabilized vacancies. But typically you will note that point defects can be present because of the way the synthesis has been made of the crystal, and for instance, impurities could get accommodated even though you did not want these impurities to be present in the crystal. Of course, in many cases we have seen we intentionally add these as an alloying element or a dopant to have some properties imparted to the crystal, like for instance we want a p type or an n type semiconductor and we add these point defects, but these could be incorporated during the growth or the synthesis of the crystal. We could have thermal and thermochemical treatments which give rise to these kind of point defects. For instance, we could have a larger than equilibrium concentration of vacancies by taking it to a high temperature and then quenching the material. And as I pointed out, how do I know that there are more vacancies present than the equilibrium concentration? Now I will have the quenched sample would have a much higher diffusivity as compared to the, of course now I am talking about a substitutional diffusivity, or a diffusion taking place by the substitutional mechanism, and this value would be much larger for the quench sample rather than for the equilibrated sample, for instance at any temperature. We are already seeing that we could actually heat in an atmosphere of a different material to or we have already seen one example, or we could even heat in a reactive atmosphere or some kind of atmosphere which would incorporate or react with my material. The other extreme possibility, the other end of the spectrum, is actually heating in vacuum, and in such cases you could some of the oxide defect or this crystal structure and formation of a defect. And there are many other methods, of course, we can consider under this thermal and thermochemical treatment. Plastic deformation is a totally distinct category wherein I am deforming the material, and this can lead to the formation of point defects. And this clearly shows up that how do I know that point defects are formed. For instance, if I am deforming copper, you will notice that the resistivity of copper increases and the conductivity falls down. And how do I restore my resistivity? I anneal the sample. You would notice that the conductivity of this deformed copper, for instance, would increase again and come back to its normal values when I what you call anneal a deformed sample. Ion implantation and irradiation is an perhaps a very good example of producing non-equilibrium concentration of vacancies. Irradiation which can be used, for instance, are electron irradiation and neutron irradiation. Electron irradiation typically we are the values which would give rise to a good what you call good dosage, which would give rise to concentration or a production of for instance vacancies would be, for instance, or an interstitial would be about 1 MeV. So, this is typically can be found in some of the 1 MeV source could be a electron microscope which typically operates at very high voltages. So, there have been electron microscope, for instance, which have capacity of 1.25 million electron volts, and these such kind of electron microscope we have to worry about the electron irradiation damage on the specimen. So, in other words, if I am analyzing a thin specimen and under one of these very high voltage microscopes, then some of the defects I may be seeing actually are not the original defects present in the material, but have actually been produced by the electron irradiation damage. So, if I have see some such defects, I have to confirm them by putting such a sample in a rather low voltage microscope to confirm that actually this is not a damage which has been produced by high voltages. Okay. And even here there are possibilities, like for instance the direct momentum transfer from the electron can lead to the formation of the defect, or it could be during the relaxation of the electronic excitations. That means if you have produced a high energy level and the system is relaxing to ground state, some of the emissions coming out could actually lead to the formation of the damage in the crystal, the formation of point defects in this case. Ion beam implantation, which is of course the technology of focused ion beam, etc., can also give rise to some of these point defects, and you can produce a large concentration of point defects in the material by irradiating with an ion beam, which would be a heavier version of some of these electron and neutron radiations. So, I have various methods of producing point defects, and having produced them, I can use experiment like a measurement of conductivity to actually confirm that you have produced a higher concentration of point defects. And typically a single point defect is difficult to see in even in high resolution microscope, or what we might call an atomic resolution microscope, but if you have a aggregation of these defects, they can be identified in a high atomic resolution microscope. We will solve a couple of examples to close this topic on point defects. So, let us calculate in this example the equilibrium concentration of vacancies, for instance in copper, and we will consider two temperatures, one temperature about 800 Kelvin, which is about slightly more than half the melting point of copper, and one temperature which is close to the melting point of copper, which is about 1350 Kelvin. So, what I am trying to calculate here is the equilibrium concentration of vacancies, that means that which has been stabilized by entropic reasons. The first thing of course I need to note is that if whatever temperature I am given has to be below the melting point of copper, because otherwise you do not have the crystalline structure of copper. So, in this case for the two temperatures for the 800 Kelvin which is being given is below the melting point of copper. So, which is about 1356 Kelvin. The enthalpy of formation of copper vacancy is about 120 kilojoule per mole, and we know that the fraction of vacancies at any temperature is given by the function n by n, which is the fraction of vacancies, where n is the number of vacant sites, n is the total number of lattice positions, is exponential minus delta Hf by RT. That means more the enthalpy of formation of vacancies, lesser the number of vacancies, higher the temperature, more the vacancies. So, what we would expect is that higher temperature, the number of vacancies would increase. That means, as you heat the metal, and we already seen even what we might call an change in length, which we will calculate in the next example. So, we can write N by N as 120 to 10 power 3, which is the joule per mole delta HF, the gas constant, because we are dealing per mole quantities and not per vacancy, and is my temperature in Kelvin. This comes out to be about 1.46 in 10 power minus 8, which is a very small fraction in terms of number of lattice positions. So, at 800 Kelvin, the concentration of vacancies is pretty small. Now, suppose I heat my sample further to close to the melting point of copper. We would notice that now my temperature is 1350, other quantities remain as before, and I get my N by N value to be about 10 power minus 5. So, there is a 3 orders of magnitude change in the concentration of vacancies, and the typical value which has been observed by measurements is of the, for very many materials, ionic and metallic materials, is of the order of 0.4, 10 power minus 4. So, you can see that even close to the melting point, the concentration, though it is not negligible, it is pretty small as compared to the number of lattice sites possible, and it is of the order of 10 power minus 4 or 10 power minus 5, which is the fraction of vacancies in a crystal, even close to the melting point. And this experiment value typically can be obtained from either lattice parameter measurements or changes in length of the material, which would be like, which one call a dialectometric measurement. We will solve another example wherein I had mentioned that if I had a material and I heated it, there are 2 reasons why it expands. One of the reasons being the normal thermal vibration, the other one being because of the creation of vacancies, wherein atoms go and sit on the surface, and therefore, the material is increased in volume and also in length therefore. So, I am asking that if I am heating a rod of copper from 0 Kelvin to about 1250 Kelvin, and the length increase about 2%, I want to know the fraction of this length increase which is coming from vacancies. So, the delta H of formation of vacancy for copper is as before 120 kilojoule per mole, and we know that copper is an FCC crystal structure with 4 atoms in a unit cell. The fractional increase in length, which is the 2% I am talking about, can be written as 0.02, which is coming from the original length L0 to the final length when I heat it to 1250 Kelvin by L0. That means delta L by L0 is 0.02 or delta L is 0.02 L0, where 0 subscript as usual refers to the original state, which is a 0 Kelvin state. And the 2 contributions to the increase in length delta are coming, as I told you, coming from thermal expansion, the normal one, which I read as with subscript TE, and from the increase of vacancies, which I read with subscript delta LV. So, the total delta L is delta LV plus delta L TE. The vacancies created by atoms migrating to the surface will lead to an volume increase in the material, and therefore, V is equal to L cube, and this length increase is what I am describing here by this 2%. So, dV is 3 L square dl. In other words, dV by V, which of course I can write, is 3 into dl by L. In other words, what I am saying is that the volumetric strain delta V by V is related to my length strain by a factor of 3. So, suppose I am talking about a length strain which is measured from this experiment, I need to convert in, which is that 2%, I need to convert into volumetric strain, which is what I am dealing with when I am heating the material using a factor of 3. This point I have to note. So, the fraction which is required to be calculated in the problem, which the question I am asking is what fraction of the increase in length is due to the formation of vacancies. The fraction I am trying to calculate is delta LV, which is the V subscript again refers to the vacancies, which I mentioned before, by delta L, which is the total increase in length, which has these 2 contributions. As before, N vacancies by N0, and I am assuming a mole of atoms here, is given by the exponential delta HF by RT, which is 1250, which is increasing from 0 to the delta T being 1250, and I get a fraction of vacancies which is about 10 power minus 6 or 10 power minus 5 in this case, close to 10 power minus 5, which I call X. Now, if 1 unit cell increase gives a volume increase of A cube, that means if 4 atoms go missing or go missing from lattice sites, go to the surface, that means that I would have a volume increase of A cube. So, 4 atoms of copper or ions of copper would correspond to a volume increase of A cube. So, NV vacancies would give a volume increase of NV A cube by 4, which is my delta V vacancies. That means the increase in volume delta V is coming from NV A cube by 4, okay. And the 4 factor, as you know, is coming from this 4 factor, which is the number of atoms in the unit cell in FCC copper. And we already seen from the previous equation 1 here, that delta V by V0 is 3 delta LV by L0, where V0 is given by N0 A cube by 4, where A cube is the volume of the unit cell, N0 is the volume of A cube by 4 being the volume of a single unit cell, and N0 being for a mole of atoms. So, delta V by V0 is NV A cube by 4 by N0 A cube by 4. So, that means that now I am trying to calculate my fraction here, delta V, delta LV by delta L, and this is delta V by V0 here, and that means I am talking about x times N0 A cube by 4 divided by N0 A cube by 4. So, this is my change in volume and this is my original volume, right, and this x is coming because NV A cube is x N0 A cube. So, this implies that 3 delta LV by L0 is equal to x. So, delta LV by L0 is, we know, x by 3, and therefore, 3 delta LV by L0 is x. So, the fraction I am trying to calculate is x by 3 L0 by delta L, which is x L0 by 3 into delta L, we know is about 2%, which is about 0.02 L0. So, this value we already calculated, the L0 cancels off in the numerator and denominator. So, the number becomes x divided by 3 into 0.02 L0, x into 3 into 0.02, and x we already know, we have calculated before, which is the fraction of vacancies which have been created, which is about 9.7 into 10 power minus 6. Substituting these values, I find the fraction of vacancies or the fraction of increase in length which is coming from purely creation of vacancies is about 10 power minus 4. So, this effect of increase in length coming from thermal expansion is about 1 in 10 power 4 as compared to the one coming from thermal vibrations. So, in normal circumstances perhaps this can be ignored, but if you want a detailed calculation of how the length increase is coming, we have to note that this is about 1 in a 10,000 effect, which is coming from increase in number of vacancies in the material. So, with this 2 examples, we have considered that how vacancies, for instance, increase in number as a fraction of lattice size as you heat the material, and also how they can give rise to an increase in length in the material, which is now related to the volumetric increase coming from the increase of vacancies in the material.